So in this video, we want to introduce the concept of permutations and combinations. These are techniques that we can use to count various items in a set. So definition, a permutation of indistinct elements x1 to xn is an ordering of the n elements. The big thing to remember when we're dealing with the permutation is that order matters. Order is relevant. So you might see words like orderings or arrangements, or you might even see the word permutation to give us this hint that the order is relevant to the question at hand. So let's do a couple of examples, and we will skip around and not necessarily do all of these. But let's do this first one. Consider a race in which the following contestants run. How many different orderings the runners could finish? So if I only have two people in the race, so in this case Al and Bo, well, Al could come first, then Bo, or Bo, then Al. And so there's only two different orderings. It's either A then B or B then A. And that's all there is, since there's only two people in this race. If I throw a third person in there, in this case the n value is 3, so I have Al, Bo, and Cliff. And notice the number of orderings is going to begin to grow relatively quickly. So this would be ABC, or ACB, BAC, BCA, CAB, or CBA. And if we notice, this is a total of 6 orderings, okay, since I threw an extra person, Cliff, into the mix. What if I had 4 runners, Al, Bo, Cliff, and Doc? So in this case, n equals 4, and so I could have A, then B, then C, then D. I could have A, then B, then D, then C. I could have A, then C, then B, then D, etc., all the way out to D, C, B, A. And I'm not going to list them all out in their entirety. I'm simply going to tell you that there are 24 orderings. And what we're doing in this example right here is we're introducing this idea of something called a factorial. I've got the definition below, and we'll look at that in just a second. But in essence, a factorial counts the number of permutations of n items. And so there were 2 runners in this race. Well, 2 factorial is 2. There were 3 runners in this second race. 3 factorial is 6. 4 runners, 4 factorial is 24. And so here's the very basic definition of what factorial says. It says that there are n factorial permutations of n elements, where n factorial is the product of n times n minus 1 times n minus 2, all the way down to 1. Now let's jump around and take a look at some examples, okay, and define what an R permutation is. An R permutation of n distinct elements x1 to xn is an ordering of an R element subset of x1 to xn. The number of permutations, R permutations of a set of n elements, is given by this formula. So n permutation R is n factorial over n minus R factorial. So let's take a look. How many 3 permutations exist from a set with 5 elements? So in this case, the n value is 5, and the R value is 3. Now, here's the idea. What does, this is as an aside, okay? What does factorial do for me? If I compute 5 factorial, that's 5 times 4 times 3 times 2 times 1, and that's 120. But let's say I have a situation where I still wish to start at 5, but I don't necessarily wish to multiply all the way down to 1. Well, that's exactly what an R permutation is. You see, factorial is great if I want to start at a given number and then automatically multiply all the way down to 1. But an R permutation is where I start at some number, in this case n, and then I cut it off, okay, at a desired number of elements. So if I compute 5 permutation 3, this is 5 factorial over 5 minus 3 factorial. This is 5 factorial over 2 factorial, and I'm going to get cute with how I write this. This is 5, 4, 3, 2, 1. 2 factorial is 2 times 1. And I notice the 2's and the 1's cancel, and so I'm simply left with 5 times 4 times 3. This would be 60. And so what this R permutation does is it allows me to cut off the factorial at a specified mark. Okay, let's do several examples. So all of these deal with permutations to some degree. Let's take a look at this second one, part B. A shelf can hold 7 trophies. How many ways can the trophies be arranged if there are 10 trophies available? So this is simply 10 permutation 7. So 10 factorial over 10 minus 7 factorial. This is 10 factorial over 3 factorial. This is 10, 9, 8, 7, 6, 5, 4 times 3 factorial over 3 factorial. The 3 factorials cancel, and so I simply multiply out from 10 all the way down to 4, and we should get 604800. Okay. 8 runners compete in the 400 meters. How many different ways can the top 3 runners finish? So this would be 8 permutation 3. So 8 factorial over 8 minus 3 factorial. So this would be 8 factorial over 8 minus 3 is 5 factorial. So this would be 8 times 7 times 6 times 5 factorial over 5 factorial. And if I were to multiply these out, so this is 8 times 7 times 6. So 336. Let's take a look at part D. How many ways can 5 distinct men and 8 distinct women wait in a queue if no 2 men stand together? Okay, so let's think about how we might go through this. Okay? So I'll just say N equals 5 men and M equals 8 women. And I want to count how many ways can these 5 men and 8 women line up, stand in a queue, if no 2 men stand together. Okay, so first let's do this. First, line up the 8 women. Since there's no restriction on how the women can be arranged, I can simply do this in 8 factorial ways. Now I'm going to draw a little picture right here. Okay? I can have a spot W1, a spot W2, etc., W3. So here's the idea. I have these 8 women arranged in 8 factorial ways. We'll compute that 8 factorial in a second. Okay? But the point is since no 2 men can stand together, then I have to put a man somewhere in one of these. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 slots to place 5 men. So if I compute 9 permutation 5, that is 15,120. And 8 factorial is the number of ways that I can rearrange the women. So 8 factorial, 40,320. Okay? So let's recall the fundamental counting rule. There are this many ways that I can place the women. There are this many ways that I can place the men. So using the fundamental counting principle, we multiply. So 40,320 times 15,120 to get 609,638,400. So this counts the total number of ways that I can arrange 8 women and 5 men in a line if no 2 men stand together. Now, let's pivot. We're going to discuss something now called a combination. Give me just a second to erase this. An R combination of indistinct elements, x1 to xn, is an unordered selection of an R element subset of x1 to xn, and it is given as follows. And there's 2 ways that we can write a combination, I guess sometimes 3. So this notation is often used, these parentheses with an N in the top and an R in the bottom. And this is read N choose R or N combination R. Or we might write C, N comma R, or we might write N C R to denote from the N items choose R of them. Now the formula for a combination, similar to that of a permutation with this one little difference right here. I have this R factorial factor that's in the denominator. What that does more or less is it eliminates the duplicates. See, in a permutation, ABC is different from CBA because this is a different ordering. However, in a combination, we would consider ABC to be equivalent to CBA because they are the exact same 3 elements and the order is irrelevant, or the order does not matter. So let's take a look at several examples. So a club has 12 persons. How many 3-person committees can be formed? Okay, well, from the 12 members, choose 3 of them. This is 12 factorial over 12 minus 3 factorial times a 3 factorial. That's 12 factorial over 9 factorial, 3 factorial, so 220. Okay. How many different 2-card hands can be dealt from a deck of 52 cards. Okay, so from the 52 cards, choose 2 of them. So 52 factorial over 52 minus 2 factorial times 2 factorial. So this is a 52 factorial in the numerator, 50 factorial times 2 factorial in the denominator. This is 1326. So what this is saying is there's 1,326 different ways that I can deal you 2 cards from a deck of 52 where the order is irrelevant. Okay, we're going to skip C and move down to D. Lotto Texas players select 6 different numbers from a set of 54. How many lottery tickets could be purchased? So the order does not matter. So this is 54 combination 6. This is 54 factorial over 54 minus 6 factorial times a 6 factorial. So 54 factorial over 48 factorial times 6 factorial, which comes out to be 25,827,165. Meaning there's more than 25 million different ways that I can play Lotto Texas, where the format is selecting 6 numbers from 54. So word to the wise, just don't buy a lottery ticket. Okay? Let's take a look at part E, maybe F. Powerball. Players choose 5 numbers from a set of 69, and then 1 Powerball from a set of 26. How many different Powerball tickets could be purchased? Okay, so this is how we're going to approach this. From the 69 numbers, choose 5 of them. Pretend they're some color. For instance, let's just say that they're white. Okay? But then I'm not done. I still have one other step in order to count the number of tickets that could be purchased. Now, from the 26, I guess you could call them red Powerballs, I have to select one of them. Now, if we remember the fundamental counting rule, it simply said, count the number of ways that you can do the first event, in this way, the 5 white balls from the set of 69, and then multiply that by the number of ways to do the second event, in this case, selecting 1 Powerball from the set of 26. So I actually have to do 69 combination 5, and then multiply that times 26 combination 1. And if I do so, I end up with 214,757,088. More than 214 million different ways that I can select a Powerball. So you can sometimes see, and I'm going to omit F for the sake of time, but we can simply see that sometimes we might say that the lottery is a tax on people who don't do math. Okay, let's do this example. This one looks fun. Okay, a pizza parlor bakes pizzas in 3 sizes, small, medium, large. Customers may select up to 3 toppings on their pizza. So they could select 0, 1, 2, and at this pizza parlor, we put a cap on it, we put a ceiling on it, and the most number of toppings that we'll let you select is 3. From a list of 12 different toppings. The question to ask is, under this format, how many different pizzas can be made? Okay, so let's take a look at several cases. So let's take a look at case 1, which I'm going to say 0 toppings. Well, if there are 0 toppings, first, there's 2 things that I have to do each time I come up and I place an order. Okay, when I place an order for a pizza, I have to select the size, and then I have to select the number of toppings. So let's say I select 0 toppings. Well, first let's select the size. So from the 3 sizes, choose one of them, times from the 12 toppings, choose 0 of them. So what is this 3 choose 1? This is saying from the 3 sizes, this is small, medium, or large, choose one of them for the size of my pizza. And then from the 12 toppings, choose how many? Well, in this case, 0. So if I go 3 combination 1 times 12 combination 0, we get simply 3. So there are 3 different ways that I could select 0 toppings. But that's only the first case. Let's take a look at case 2. In case 2, let's say that I select 1 topping. And hopefully we'll see a pattern emerge. If I select 1 topping, we'll first select the size. From the 3 sizes, choose 1, times from the 12 toppings, choose 1. I'm only putting 1 topping on this pizza. And if I go 3 combination 1 and multiply that by 12 combination 1, we get 36. So there are 36 different potential pizzas that could be made with 1 topping. Case 3. Case 3. Let's say I have 2 toppings. And you can see where this is going. From the 3 pizzas, choose one of them, From the 3 sizes, choose one of them, times from the 12 toppings, choose 2. So 3 combination 1 times 12 combination 2 would be 198. And now lastly, let's take a look at case 4. 3 toppings. Okay. From the 3 sizes, choose one of them, small, medium, or large, times from the 12 toppings, choose 3 of them. So 3 combination 1 times 12 combination 3 is 660. And so now we desire to sum up all of these cases. In essence, there are 3 ways to do 0 toppings, plus 36 ways to do 1 topping, plus 198 ways to do 2 toppings, and 660 ways to do 3 toppings. If I sum these together, I get 897. Okay? So under this format, where I first select the size of the pizza, small, medium, large, and then I select the number of toppings, 0, 1, 2, and I put a cap on it at 3, then there are 897 different combinations, per se, that we could make under this format. Now, let's ask, what would I need to do if I didn't put a cap on the number of toppings? Because some of us might ask, okay, well, what if I want to have 4 toppings? Or 5 toppings? Or what if I want to have all 12 toppings? Then what would I do in that case? Well, that brings us down to this next theorem that I wish to briefly discuss. So, theorem, the sum of all possible combinations of n distinct elements is 2 to the n, meaning n choose 0 plus n choose 1 plus n choose 2 plus n choose n equals 2 to the n. So under this pizza situation, okay, if you notice what we had 3 times 12 combination 0 plus 3 times 12 combination 1 plus 3 times 12 combination 2 plus 3 times 12 combination 3. And that's what we did under this pizza example. But let's say I continued it all the way out and I did plus 3 times 12 combination 12. Well, if I notice that this 3 is common to all of these terms, so I could factor this 3 out, and then I would have 12 combination 0 plus 12 combination 1 all the way out to 12 combination 12. Well, my claim is this. Using this little theorem right here, okay, n choose 0 plus n choose 1 all the way out to n choose n is simply 2 to the n. So this right here, this 3 still stays factored out, sums up to be 2 to the power of 12. 2 to the power of 12, which would be 3 times 2 to the 12th power is 4096. And if I multiply those together, that's 12,288, which simply would mean the total number of pizzas that I could make, including sizes, small, medium, or large, and number of toppings, 0, 1, 2, 3, 4, all the way up through 12. So this is a very useful theorem right here that computes the sum of combinations from n choose 0 all the way up to n choose n. Okay, let's erase this, and then we'll do possibly one other example. Consider drawing 5 cards from a deck of 52. Count the following number of hands. Okay. So, total 5 cards. Well, this is simply from the 52 cards, choose 5 of them. From the 52 cards, choose 5 of them. Remember, this is 52 factorial over 52 minus 5 factorial times a 5 factorial. This is 52 factorial over 52 minus 5, what's that? That is 47 factorial times 5 factorial. So 2,598,960. Or 2 million, more than 2.5 million ways to draw 5 cards from the 52. Okay, what about all 5 hearts? Okay, well, to answer some of these questions, I have to know the makeup of a deck. So if you don't know, there are 13 hearts in the deck. So from the 13 hearts, choose 5 of them to be in your hand. I'm just going to write out the answer. That's 1287. I assume by now you should be able to run it through this formula. The idea is just through the thought process of how we set up these combinations. Okay, let's compute the probability of 3 of a kind. And when I say 3 of a kind, that means 3 of a kind exactly. So that means 3 cards of the same denomination, so like 3 2s or 3 3s or 3 4s or 3 5s, and then the other 2 cards are of 2 different denominations, okay? So this is how we would think this one through. From the 13 denominations, Okay, so the 2 to the ace. Select one of them to be the denomination where my 3 of a kind is going to be in. From the 4 cards in that suit, so for instance, from the 4 fives, choose 3 of them to be in my hand. But now I still have more cards to select. From the 12 denominations that are not the denomination that I want my 3 of a kind in, select 2 of them. So maybe my 3 of a kind was in fives, and so I have to select 2 different denominations from the 12 remaining. From the 4 in the first denomination, choose one of them. And from the 4 in the second denomination, choose one of them. And what the fundamental counting principle says is I would just multiply all of these together to give 54,912 is the number of different ways that we could draw 3 of a kind. Okay, 2 pairs exactly. Okay, so what do I mean when I say 2 pairs? So that means a pair from one denomination, a pair from a different denomination, and then the 5th card doesn't belong to either of the first 2 denominations. So 2 alike, and then the 5th one is just in some other denomination. So how would we work this one through? From the 13 denominations, choose 2 of them to be the denominations that have my 2 pairs. From the 4 in the first denomination, choose 2 of them. And from the 4 in the second denomination, choose 2 of them. Okay, so I've got my 2 pairs set up, but now I have to select the 5th card. Okay, so let's think this through. I don't want it to be from the denomination of either of these pairs. Okay? So from the 11 remaining denominations, because the 13th and the 12th are the denominations where my pairs are coming from, but from the 11 remaining denominations, choose one of them to be the denomination where this 5th card comes in. And then from the 4 in that denomination, select one of them to be in my hand. So if I multiply these together, I get 123,552 different ways that I could get 2 pairs exactly. Okay. Lastly, let's do a full house. And a full house, colloquially, in poker terms, is 3 of a kind and 2 of a kind. Okay. So let's compute this. So from the 13 denominations, choose one of them to be the denomination where I get 3 of a kind from. From the 4 in that denomination, choose 3 of them. Now, I have to select my pair, or my 2 of a kind, to go with it. From the remaining 12 denominations, choose one of them to be the denomination that my pair comes from. And then, from the 4 in that denomination, choose 2 of them to finish out my hand and make a pair. And the fundamental counting rule says I multiply all of these together to give 3, 7, 4, 4. And so this counts the number of ways that I can get 3 of a kind and 2 of a kind, or what we would simply call a full house in poker. And now the idea is this. We can easily see that if I just look at C, D, and E, okay, which of these has the least Number of outcomes, well, that would be a full house. That is why a full house, okay, is a more valuable hand, or is a hand that beats a three of a kind. Why is that? Well, the number of outcomes is fewer, and we haven't talked probability yet, but the probability of this event will be less likely. Therefore, we reward full houses over three of a kinds. Now, there are fewer ways to get three of a kind than there are to get two pair. And so that's why a three of a kind beats a two pair hand. And so there's a lot of counting going on when I take a look at cards. I often say that a deck of cards is a playground for probability questions, but these were some very good ones to kind of get us started, get us thinking about combinations with respect to counting.